the Fourier series. So Fourier series is a method of representing functions which is some particular period called t, capital T, big T. So we have learned that for general T can be represented by the following series. Plus Bn sine t over 2 pi n t You don't have to memorize, but I happen to memorize it. So A0 is basically the average of a function over the period. Half period to minus half period to half period divided by t. That's average, right? Average of function over the period. An is 2 over t, ft cosine t over 2 pi and t dt. Bn is 2 over t ft sine 2 pi and t over t dt. So basically we need to calculate the two coefficients, an and bn. But we are usually quite lazy, so it would be nice if you can have a method to have just one coefficient. Okay, let me just put it down to the So we are going to try to find the way that if copy and paste. But you can actually combine these coefficients together using the Euler's formula. So exponential I 2 pi n t over t. You can represent using the Euler's formula, right? Cosine 2 pi n t over t plus I sine 2 pi n t over t, right? And exponential minus I 2 pi n t over t is cosine 2 pi n t over big T minus I sine 2 pi n t over t. So the cosine and sine can be written as a combination of exponential I something plus exponential minus I something. So cosine 2 pi n t over t is basically 1 over 2 exponential I 2 pi n t over t plus exponential minus I 2 pi n t over t. And Probably I should write sine a little bit smaller letter. 2 pi and t over t is 2I over exponential I 2 pi and t over 2 minus exponential minus I 2 pi and t over big T. So we can substitute this expression for cosine and sine in terms of exponential I and exponential minus I something into the definition of the coefficient an and bn. So I'll just write it down. An 2 over t minus t over 2 minus t over 2 ft cosine t over 2 pi and t dt is two over t times ft 1 over 2 exponential I 2 pi and t over t plus exponential minus I 2 pi and t over dt. On the other hand, bn is 2 over t minus t over 2 t over 2 ft 2 over exponential I 2 over e pi and t. Oh, wait a minute. Just so actually I don't have to calculate this at this moment. 2 over t minus t over t ft sine 2 pi and t over t dt, and ft can be written as a0 plus n equal to infinite an cosine t over 2 pi and t plus bn sine t over 2 pi and t. Right? So we replace cosine and sine in the summation sign. An 2 over exponential I 2 pi and t over t plus exponential minus I 2 pi and t over t plus bn 2I exponential I 2 pi and t over big T minus exponential minus I t over 2 pi and t. So if we continue to this, so we started with the original definition of Fourier series, right? And then we replaced cosine and sine using Euler's formula. going to be written as a0 plus n equal to 1 over infinite one over 2 an plus bn over I exponential I 2 pi and t over big T plus n equal to 1 to infinite an minus I over bn exponential I minus I 2 pi n t over big T. So let's define Cn. Cn as 1 over 2 an plus bn over I, or an minus ibn. Then the other coefficient, an minus I over bn, which is given by an plus ibn, can be written as Cn to the complex conjugate, right? So the Cn and the other coefficient is already difference is the sign of the minus I. So that can be interpreted as Cn with the complex conjugate, which is 컬레복수수, right, in Korean. So Ft can be written as the following: A0 Cn exponential I t over 2 pi n t plus n equal to 1 to infinite Cn complex conjugate exponential minus I t over 2 pi n t, right? So this apparently this series is a little bit less manageable because it has a minus sign. So if we change the index by minus n into something, some other index, so we can change this by minus n into some other integer. Then the second summation can be represented as Cn exponential I 2 pi n t plus, now summation must be for the minus integer, right? So m is starting with minus infinite to minus 1, right? Then we have minus m to the complex conjugate exponential I t over 2 pi n t mt. Initially, we define Fourier series from cosine and sine, but we can actually change exponential I and minus I with the following coefficient. term will be Cn to the complex conjugate, right? Because there is a change of sign and the imaginary number I. So the original series can be rewritten as Cn exponential I 2 pi n t over t plus n equal to 1 to infinity. But it's a Cn to the complex conjugate with the exponential minus I 2 pi n t. But somehow it's a little bit inconvenient because it does have plus, it does have minus. But if we notice that this minus n, if we replace by some other integer n, then summation can be, instead of n equal 1 to infinity, we can sum over minus infinity minus 1. But instead, we have C complex conjugate with the minus n. So we follow this up to now. Yeah. Oh, sure. Summarize a little bit. So ft a0 plus n equal to 1 to infinite cn exponential I 2 pi n t over big T plus we have a different summation. M is minus infinity to minus 1, right? C minus m complex conjugate exponential t over I 2 pi m t. So let's consider Cm. That is an plus 1 over I bn, right? Over an minus I bn, which is 2 over t minus 1 over t ft cosine 2 pi n t over 2 dt minus I 2 over t ft sine 2 over 2 pi n t over dt, which can be combined them together with 2 minus 2 t over 2 ft exponential, this is big T, this is big T, t over I 2 pi n t dt. Right? So I'll just summarize. Right. 2 over 2 over 2. Cn. Right. Plus or minus. Plus. So you can rewrite the original period series as A0 plus Cn with the same sign, but coefficient is C minus m with the complex conjugate. And take a look at this an and bn. The Cn is given by 1 over 2 cosine and sine. So this cosine minus I sine can be together as exponential minus I. This Cn. So we define Cn as an plus bn over I as a Cn. Oh, right. Sorry. So let me see. I must have confused. So thank you. I made a mistake. So we have 1 over 2, right? So we have 1 over 2. And we have 1 over 2, 1 over 2, 1 over 2, right? Now it's okay? Oh. Right. Very good point. So I made another mistake when I take the base. So basically it's 1 over 3, right? So then these two cancel to each other. But 2 over t exponential minus t over 2 to t over 2 ft exponential minus I t over 2 pi and t dt. Oh, this is not, this is Cn. Let me check the formula. So from this, if we take a complex conjugate, what do we get? 2 over t ft exponential plus I, right? 2 pi and t over t dt. On the other hand, the C complex conjugate minus n is 2 over t over t ft exponential minus I, right? Because we are going to put minus n here over t dt. And it turns out to be the same as to what? Cn, right? So ft is a0 plus do we have Cn exponential Cn I 2 pi n t over t plus n equal to minus infinity to minus 1 Cn exponential I 2 pi n t, right? So this one actually C minus n complex conjugate, the same as Cn. Yeah. Here. So we have actually 1 over 2, 1 over 2, 1 over 2, right? So now we are in good shape. So when n is equal to 0, C0 is what? 1 over t minus t over 2, t over 2. Exponential 0 is 1, right? So ft dt, which is same as what? A0. So we can represent the Fourier series just using one coefficient, Cn. Coefficient. So Cn is 1 over t, right. So therefore, Ft can be written as, now we can sum in the single sum, minus infinite to infinite, Cn exponential I 2 pi n t over t, right? And Cn is given by 1 over t minus t over 2, t over 2, ft exponential minus I 2 pi n t over t dt. Let me just double check just in case if I missed any. So this is what is called complex Fourier series. So complex Fourier series has an advantage of using just one coefficient, Cn, but of course there is a price you have to pay because you have to use complex numbers. So that's the price that you have to pay for simplification of the coefficient. So I didn't make any mistake here, right? This is good to know. So let's do some simple example. So before I proceed, right. Perhaps we have the following. Same problem. Minus 1, 1, 1. Two, 3. So for this problem, the period is 4. So coefficients can be calculated very simply. 1 over 4 minus 1 to 1. Ft is equal to 1, right? So exponential minus I 4 over 2 pi I n. Oops. 2 pi n t dt. 1 over 4 exponential minus I 2 over pi n t dt. So 1 over 4 minus pi n over 2 I minus 1 to 1 exponential. Exponential minus I pi n t over 2 minus 1 to 1. So that is this 2 cancel 2. 2 pi n over I exponential minus I pi n over 2 minus exponential I pi n over 2
마이너스 2부터 2까지.
응?
인테그레이션이 마이너스 2부터 2까지.
Yeah, minus 2 to 2 pi is 0. Right, you're right. Minus 2 to 2, but this for this region, the ft is 0. Here it's 2. You don't have to worry about that. This is minus I 2 pi n exponential I pi n over 2 minus exponential minus I pi n over 2, which is twice I times sine pi n over 2. So it is 1 over pi n sine pi n over 2. Straightforward, right? To calculate that. So for homework, maybe I can give you the following homework. I'll let you copy. Homework. Perhaps. Which is 1 minus t squared. I think that can be good homework for you. Homework number 1. Another homework number 2. You don't have to give it to me. Just do it for your final exam. Okay. I'll be a little bit more generous. Let's say 4. Something like this. So let's change the period into the 4. That will become better for you. Otherwise, we will have a 3 pi over something a bit complicated. this can be two very good homework for you to do. Most likely, I think I can give you one of those for the final exam. To draw the homework problems. So let's write down so what if t goes to infinite? So this is typical aperiodic function, right? So normal functions, you can regard that as repeating itself for infinite period, right? So at the end of the world, you start. So we can actually take a look at the ordinary functions from this point of view for the infinite period. Then 1 over t goes to 0, right? Definitely. So let's define w as index 2 pi n over t. Wn plus 1 minus Wn is 2 pi over t, right? So we can say 1 over t is some small delta n. Then Wn plus 1 minus Wn is some delta omega. Then you can say delta omega divided by 2 pi, same as delta n. And we say 1 over t and some integration, delta n. Summation over n can be when t goes to infinity. Then if we divide by t, we can really consider some integration. Small change of index over the t. n divided by t is a very small number, right? So you can think of this as some integration, right? So same as Newton invented integration out of the differentiation. So you can regard this as a summation of n divided by t. It's actually some small delta, right? So this is considered as integration. And the coefficient times Cn, we can regard this some function of omega. So, using this notation over here, using this notation, right? From here. So this is plus initially written as minus infinity to infinity Cn exponential minus I 2 pi n t over t becomes 1 over t Cn exponential minus I 2 pi n over t and we can regard this is omega and this considers t omega. So this is Tn is actually 2 pi over d omega. I mean 2 pi delta n delta omega. So for infinity period, ft can be written as 1 over 2 pi minus infinity to infinity d omega some function exponential minus omega t. Right? So we are considering a limiting case, limiting process. Then summation over n divided by t can be written as some integration over delta n. But delta n, integration over delta n can be written as a delta omega divided by 2 pi. And Cn we have original formula for calculating the Cn, right? Cn, so I think I made a mistake of sign, minus. So it has to be plus and plus. Check. I've been trying to be careful, but still making mistake. Defined as 1 over t minus infinity to infinity ft exponential I t over 2 pi and t. So Tcn, which become actually f tilde omega, is minus infinity to infinity ft, and this becomes omega, exponential I omega t dt. If we take the period t goes to infinity limit, this complex Fourier series can be written as some integral representation, which is called Fourier transform. So Fourier transform is a method of representing any function with infinity period. So fine, and Cn must be minus, right? So this must be minus. So minus ft 1 over 2 pi minus infinite to infinite f omega exponential minus omega t dt and f tilde omega minus infinite to infinite ft exponential I omega t. This is d omega dt. This is called the Fourier transformation. And Fourier transformation is a very important mathematical tool to describe a system response or communication, etc., in many fields. So before we proceed, maybe you can take a break for a few minutes. Probably need to check. So this is plus, this is minus. Let's say a very simple case. This is not a periodic function, right? But we can regard this, repeat this after infinite. Then the Fourier transform is minus 1 to 1 exponential minus I omega t dt, right? So minus I omega exponential minus I omega t minus 1 to 1 minus I omega exponential minus I omega minus I omega, which is I omega exponential I omega minus exponential minus I omega 2 over omega over sine omega. Let you copy. Okay, so ft, we define ft as 1 over 2 pi minus infinite to infinite f tilde omega exponential I omega t t omega and 1 over 2 pi f t prime exponential minus I omega t prime t t prime times exponential I omega t t omega. So this is 2 pi ft prime exponential I omega t minus t prime t prime t omega. But we can exchange the dt integration and d omega integration, then the following 1 over 2 pi exponential I omega t minus t prime d omega ft prime dt prime is ft, right? So we define within the bracket that this function as delta function or direct delta function. So delta function is the following property. I will let you copy. Because in this integration, whether this, another question is whether this is exact, also has a property of delta function, right? You can see, you need to see that. So this integration with minus L to L, and then take the limit of L goes to infinite, and whether this becomes delta function. So let's see. Oh, delta t infinite or 0. But delta t dt is equal to 1. Ft delta t dt is f0. So sometimes it's called the generalized function or distribution. There's too many functions, right? Delta function is the delta function is only remaining when the argument is 0. So when t is equal to 0, it's infinite. Or otherwise 0. T equal to 0. And if we integrate, this is equal to 1. If we integrate with ft, then it's 0. So if we have ft prime delta t minus t prime dt prime is ft. So certain functions has this property. For example, I'm considering, let's say, some function g epsilon t as 3 over 4 epsilon 3 t squared. another function. So when t is equal to 0, what happens? G epsilon t becomes 3 over 4, 1 over epsilon, right? So it goes to infinite, right? When t is not equal to 0, what happens? If epsilon approaches t, then g epsilon t goes to t is not equal to 0, and epsilon is approaching t, then the denominator is 0, so it becomes 0. If we integrate this from minus epsilon to epsilon, g epsilon t dt, what do you get? 3 over 4, 1 over epsilon q. D epsilon, right? Minus 1 over epsilon cube, 1 over 3, t to the cube, epsilon minus epsilon, right? So that is 2 minus 2 over 3, 3 over 4, 3 over 4 is equal to 1. So this is one function that approximately represents delta function. So this can be an approximation of delta function. But my question is whether this can be, so I'm actually, let's say GL T as 1 over 2 pi minus L to L exponential I omega T, T omega. And see whether this is a property of a delta function. So this is 1 over 2 pi I omega exponential I omega T L to minus L oh no, it's not T, it's IT. So 2 pi IT exponential I omega ILT. LT minus exponential minus LT. So 1 over 2 pi times twice over T over sine LT. So we divide by L and multiply by L. So it becomes L over pi sine LT over sine LT. This is L over pi. So GLT L over pi LT sine LT. When t goes to 0, what happens? You can apply L'Hopital theorem, right? So this goes to 1. So it becomes L over pi. So as L goes to infinite, GL0 goes to infinite, right? When GLT is equal to 0, that means LT must be n pi. So T must be L over n pi. So this function GLT will look pi over L minus pi over L. This is L over pi. Something like this. And let's calculate this area. This area is what? 1/2 times 2 pi over L times height is equal to 1, right? So if you integrate this function, the area goes to 1. And if L goes to infinite, this very narrow function with a very high, very big height, right? So it becomes delta function. As it becomes something like this, infinite, as L goes to 0. Infinite. Today you have to have observed the several concepts. The first concept was we can actually represent Fourier series in complex domain, right? Complex Fourier series with one coefficient C. And then using this complex Fourier series, we can represent any function as a limit for the infinite period, which is defined by Fourier's transformation. And thirdly, we also define the Dirac delta function, which is a generalized function with infinite bound when argument is 0 and is 0 otherwise. And if you integrate over the delta function, area is 1. And since today is actually supposed to be the compensation week, the 보강 주간, so probably we can stop here today. What do you think? So we will continue our discussion next week.